So today we're going to be looking at how to quantify our descriptions. So we're going to be describing our data and we're going to actually use numbers, measurements of center and actual values instead of just kind of describing the overall shape and that kind of thing. So the first thing we're going to look at is mean. Mean is the same as you've always learned. Okay? We add up all of our values, all of our data points from our set. Okay, and we divide that by the number of observations. So on your formula charts, this is what mean will look like. Mean will be represented by X with a bar over it. Okay, and that means that it is the mean of a sample. Remember, notation is really important. Okay, notation in what you say is very, very important. Okay, and so X bar is the mean of a sample. If you actually had all the data for the entire population, then you would use mu, which is the mean of the population. Okay, it's this weird little U with like kind of a front tail on it. Okay, our mu. So that would mean that we have all of the data points that are in the entire population and we're getting the true mean of the population, where X bar is the mean of a sample, which is what we're going to see more often. So like I said, right here is what you're going to see on your formula chart. Okay, the X with a little I next to it just means that you're doing all of the data points in that set. Okay, so all of the data points in that set there. N is our number of observations. Okay, so that's what N stands for here, is our number of observations. And then you know that that is the Greek letter for sum. Okay, sigma is the Greek letter. The Greek letter sigma means sum. Okay, so add them all up, it's average. Mean is average. So we've got a quick example right here, calculating the mean. You've got a stem plot of travel times to work for a sample of 15 people from North Carolina. Okay, right here, so we've got this stem plot. So it asks the mean travel time for all 15 workers. Okay, so when we're calculating the mean for this, I'm not gonna write it out because it'll get too messy. You're gonna calculate it just like you normally would in any math class that you've ever taken. But remember how your stem plot works, right? You're going to, let's just kind of move some stuff around here so you can see better. Okay, so remember you've got all of your data points coming from your stem plot. Okay, my stem here, I've got my key right there. So I have data points of 5, 10, 10, 10, 10, 12, 15, 20, 20, 25, 30, 30, 40, 40, and 60. Okay, so I'm going to add all of those data points up, and then I'm going to divide by 15. And so I get my mean time, my mean travel time is 22.5 minutes. Okay, again, you notice they put context in here. They didn't just say the mean is 22.5. Okay, the mean travel time for the particular samples, they identified the sample, 15 North Carolina workers, and then you notice they put units. Okay, so you cannot just write the mean is 22.5. My mean travel time and describe your sample and then put your units on there. So then part B asks you to exclude the 60-minute one because that possibly could be an outlier. And so now realize, that you only have 14. So you'll be dividing by 14 now instead of 15. Okay, and now we get a mean travel time for these 15 North Carolina workers at 19.8 minutes. Okay, and so having that one observation that is significantly higher than the others really can move the mean. It's shifting the mean. It shifts the mean by 2.7 minutes. Okay, what that tells us is that mean is what we call a non-resistant measure. Okay, so mean is a not resistant measure, meaning that outliers or very large or very small values, they can affect it. They're going to pull it and they can change it. So mean is sensitive to those sways of those higher values, those really high values, and as well as really low values. You could have had a stem plot here that was skewed left with people that had really long drives to work, and then one person that had a 5-minute drive, and that would sway your mean as well. So it is a not resistant form of measurement. Think of mean as your balance point. Okay? Mean is your balance point for the distribution of the data. So the area that the data is distributed over, that length that the data is distributed across, okay, the mean is the balance point for that. And if you have a piece of data that is really high or really low, that will shift or pull our balance point. Okay? Hopefully we'll be able to get to see more of this in class. I'm hoping to get to do an activity that will kind of show that a little bit more. Okay, so our next measure is median. Median is the exact same as it has been all the times you've talked about it in math. It is our midpoint of our distribution. We have about the same number, the same amount of values that are smaller and the same amount of values that are larger, the same number of values. Okay, when you're calculating mean, all you need to do is arrange all your data points in order from smallest to largest. Remember, if it's a data set with an odd amount of numbers, right? If I have a data set that looks like this with an odd amount of numbers, my median will be right there in the middle, right? If it has an even amount of numbers, I take my 2 points in the middle and I average them together for this one. That wouldn't be a very difficult average. So looking here, it's asking us to calculate the median for these 15 North Carolina workers. They already put the data set in order for us. Well, there are 15 workers, so this is an odd set. So our median would be right here at 20, where I have 7 values below and 7 values to the left and 7 values to the right. Not necessarily above and below. You'll notice right here I have a value of 20, which is the same. Okay. As for the even set, so down here at the bottom, we have a set of North Carolina workers. This time I've got 20 workers here. And it's, again, looking at the travel time in minutes of these randomly chosen 20 workers. The first thing it asks us to do is make a stem plot of the data and to be sure that we include a key. Okay, so you can see your stem plot down here. Okay, remember we made sure to include a key as to what the stem plot means. Okay, we didn't split our stem here because we didn't have bunches and bunches of, numbers that had one particular stem. Okay, and then it asked us to find the median by hand, so not to plug it in our calculator, to find the median by hand. By making the stem plot, you did basically arrange the data points in order, so you don't need to lay them back out again. Okay, you've got 1 data point, 2, 3, 4, 5, 6, 7, 8, 9, 10 there at 20. And so data point 11 would be at 25. So to find the median here, we would add those 2 data points together. That's our center pair. We have 9 observations below them and 9 observations above them. Add those 2 together and then divide by 2, and we get our median here of 22.5 minutes. So our median, unlike our mean, our median is resistant to the data points. For example, if I had a 5-set data point sample and it had 1, 2, 3, and then it had 6, and then it had like 25. Okay, that 25 would make a big impact on my mean for this data set, but my median is still going to be right there at 3. Okay, regardless of the outlier. So our median is going to be resistant. On a data set where our distribution is roughly symmetric, our mean and our median and your median are both going to be pretty close together there right here at the peak, because I don't have any outliers that are pulling that mean in any particular direction. On data, though, however, that is skewed, our median is still going to be close to the peak. Okay, so we're still going to have a median really close to the peak, because again, when it goes so high up here, I've got more data points in that area. And again, median is just about the number of data points on each side of the particular point. Our mean is going to end up a little bit more down the tail. So for instance, in this left skewed data here, our mean would be a little bit further down the tail. Whereas if we had right skewed data, right, again, our mean would be a little bit further down the tail because it's getting pulled by these extremely high values. In this left skewed data here, it's getting pulled by the extremely low values, but we still have the same number of data points. So our median is still kind of in the middle or close to the top of our peak, but our mean will be pulled down the tail a little bit. So when you're choosing whether to use mean or median, usually data that's extremely skewed, you'd use median more often for your center. Data that's not quite as skewed, mean gives us a good representation of our center. Let's look at these questions really quick. I would strongly suggest that you pause and see if you can quickly answer these questions before we go through the solutions. Okay, see how you're doing so far. So the first one, again, here we've got our stem plot again for our 20 randomly selected New Yorkers. Remember, the median for them, when we looked at it earlier, was 22.5 minutes. So based only on the stem plot, would you expect the mean travel time, so don't calculate the mean, based solely on the stem plot, would you expect the mean travel time to be less than, about the same, or larger than the median? Okay, well, if we take this stem plot, okay, we get our data set that's going to look like this. Okay, so this data set is going to be skewed to the right. So if it's skewed to the right, remember our median is going to be located around the peak, and our mean is going to be a little bit down the side of the tail, down the tail. Well, if we're skewed right, things are getting larger as we move to the right, so we would expect our mean here to be a little bit larger than the median. And the reason why we would expect that mean to be larger is because this data is skewed to the right. Okay, the second one asks you to find your calculator to find the mean travel time. Okay, and you're double checking if your answer was right in number 1. So our mean travel time in this particular set is 31.25 minutes, which is definitely greater than our median time of 22.5 minutes. And then the third question here is asking if the mean or the median would be a more appropriate summary of the center of this distribution of drive times. And then we have to support it. Okay? Well, in this particular case, again, our median is going to be a better measure. So our median would be better, again, because this data is skewed. The median would be a better measure of the center of distribution. Okay, so let's look at some measures of spread now. So the first one is range. Okay, so when we're calculating range, you need to keep in mind, remember that range only focuses on the highest value and the lowest value. So outliers can have a big impact on range. Range is going to be like the mean, or it is going to be considered not resistant. So range is supposed to encompass my entire distribution, from one end to the other. So if I have a data set that looks like this, so if I have a data set that looks like this, my range here is 14. Okay, remember, my range is not 1 to 15. Okay, my range is 14. It is one value. Okay, and so that would include only here and here. So if one of these was a big, huge outlier, let's say this wasn't 15 anymore, and let's say this was 50. So now my range becomes 49. Okay, and that outlier is having a major impact on my range. So to help avoid that, we can look at quartiles. And when we're looking at quartiles, we are basically looking at the middle chunk of the data, the middle 50% of the data. So we have 7 data points here. So here is our middle data point right here. Okay, and so basically what we would be looking at is the data from here, so the middle of this side, and then the data from the middle of this side. So when we're looking at quartiles, we are looking at this chunk of the data, which would then eliminate your outliers. So when you're looking at quartiles, you have a more resistant form of measurement. Okay? So let's look at how we find these quartiles to calculate your quartiles. So you have the first quartile, the second, and the third. Okay? The second is going to be your median. Okay? This would be kind of basically this is your 50% mark. Okay? Over here is your 25% mark, and over here is your 75% mark. Okay? And so you're looking at the data between this 25 and 75. Okay? This is 50% of the data. I've got 25% of the data left over here and 25% of the data left over there. Okay? So the first quartile is going to be, let me clear this up a little bit so you can see. Okay, so our first quartile is going to be the median of the observations that are to the left of the data set. So again, if I have a data set, well, here, let's use this. This is our data set of those North Carolina drivers. If I have room to write it all. Okay, so there's the data set of these North Carolina drivers. And right here in the middle, okay, so this one right here, this was my median. Remember, this was an odd data set. There are 15 points in this data set. So when I'm finding the first quartile, I am looking for the median of the numbers to the left of the median of the whole set. Okay, so 20 is my median of the entire set. And so when I'm looking for the first quartile, I am looking for the median of the numbers that are to the left, which is going to be this one here. I've got 7 numbers to the left, and so this one right there is in the middle. So this would be my Q1 value. When I am finding my, okay, so my median is my Q2. And so when I'm finding my third quartile here, again, I'm looking for the median on the data point, the median of the data points that are to the right of the median of the whole set. So this one right here, that would be my third quartile value. Once you find the first and the third quartile, you can then find your interquartile range, or your IQR. Okay, so it's another, again, it's a range, so it's only going to be one number, but this is the range of data, remember, in this 50% here. It's the range of the middle 50% of the data. That's what you're finding with this IQR. And so when you calculate IQR, you are just taking your Q3 minus your Q1. So your third quartile minus the first quartile. Okay, and so in this particular case, it would be 30 minus 10. And so now we get a range of 20 as opposed to a range of 55 if we're looking at the entire data set. Okay, so let's look at this example real quick. So this is the 20 New Yorkers. So we've asked to find and interpret the IQR, or the interquartile range. Okay, so again, remember that our Q1 is found by finding, so here's our median. This is an odd data set, or an even data set. Remember, there were 20 values here. So my median is right here in the middle. My median isn't an official number in my data set. So now when I'm finding the Q1, I'm looking at all 10 of these. And then when I look for Q3, the third quartile, I look at all 10 of these to the right. okay, because my median is not an actual set. It's not an actual number in the set. So like normal, okay, I'd find my median like normal. So my Q1 here is 15. Okay, my first quartile here is 15. Okay, I've got 10 data points, so I need in between the two 15s there. And then my Q3 here is 42.5 because I have 10 data points. And again, I need in between these middle two, which is 40 and 45, because I have an even number here. When I find my IQR, I take my 42.5 minus 15. Okay, I get 27.5 minutes, but I am not done because I did not do the interpretation. The interpretation is that the range, so I just need to define what this means. What is that 27.5 minutes? Well, that 27.5 minutes is the range of the middle half of the travel times. And again, using our context for these New Yorkers, for the New Yorkers in the sample. Okay, so it's just telling us what the range is of this data right here. So if I had any outliers, they wouldn't be factored into that range. Okay, so now let's look at a rule for actually identifying outliers using this IQR. Okay, so before we would talk about potential outliers. So now we have kind of a hard and fast way to determine if they were an outlier. So we can determine if an observation or a data point is an outlier by using what we call the IQR rule. And so if it falls more than 1.5 times the IQR above the third quartile, I can't talk, or below the first quartile. So basically, for instance, in the last set, okay, we had an IQR of 27.5 minutes. So if I wanted to know if the other travel times were outliers, I would take 27.5 times 1.5, and I would take that value, which is 41.25, and then I would take that minus my first quartile, okay, and I would above my third quartile. And if I had any values that were bigger than those or smaller than those, then I would say that those values are definitely outliers. Okay, so let's look at this example. This time we're back to those North Carolina data set with that set of 15 workers. And we had talked before that the 60-minute drive was a potential outlier. So using this method, we can determine if it is for real. Okay, so in this data set here, we've got a Q1, or our first quartile is at 10, if you remember, and the second one is or the Q3 is at 30. So our IQR here was 20. So 20 times 1.5 gives us 30. Okay, and so what we're looking at here, okay, is that any value that is greater or less than that added to the Q3 and then subtracted from the Q1, okay, would be considered an outlier. So Q3 plus 30 plus 1.5 times the IQR, okay, is 60. And then Q1 minus 1.5 times the IQR. So minus 30 is negative 20. We don't have anybody that has a negative 20 commute, so that none of the lower commutes would be considered outliers. Okay, but in this case, we do have a 60-minute commute. Okay, well, that 60-minute commute is not an outlier. It is right at the mark, but it has to be greater than 60, not greater than or equal to 60. So that one officially is not an outlier. Any bigger, though, and it would be. Okay, so let's tie this all together with box plots and the 5-number summary. So our 5-number summary is basically all that is our minimum, our Q1, median, Q3, and a maximum. Okay, so we're giving these 5 numbers that will give us our basic distribution, and divide that distribution in quarters. Because remember, the minimum essentially would be at 0, right? If you break it into percent, right? Because we talked about this right here being the middle 50%, right? So this will be at 25%, 50%, 75%, and 100% of our data points. So this would encompass kind of the entire distribution. And we can see this on a box plot. And I'm hoping that you guys remember how to draw box plots. I'm pretty sure you've been taught how to draw these before. Okay, remember the box plot is the one that looks like this, right? Something like that. Whiskers, right? So when you draw your box plot, remember you've got your central box and it is drawn. So the box goes from Q1 to Q3. Okay, the line right here in the middle represents the median of the entire set. So that's our line right there in the middle of the box. Okay, the whiskers, okay, so out here on the edges, right, these are whiskers. These go to the smallest and largest observations that are not outliers. So this is, right, this value right here is my IQR, right, times 1.5 plus the Q3, right, because anything past that would be an outlier. And this one would be Q1 minus my IQR times 1.5. And again, my outliers would just be out. You can put your outliers out there as individual little dots if you had an outlier. Okay, so you could use a star, you could use a little square, okay, but they'll have a special symbol, whatever you choose, out there past that. Okay, so let's run through this example real quick. Like I said, I'm pretty sure you've done this before. Okay, so in this particular example, we're making a box plot based on data from Barry Bonds and his home runs. Okay, so here's the data for the number of home runs that Bonds hit in each of his 21 complete seasons. So the number of home runs over the entire season. So the data set is already put in order for you. Okay, so let's get some more room on here. So the data set is in order, but we need to mark out our Q1 and our Q3 to be able to draw a box plot. Minimums and maximums if we're doing our 5-number summary. So our minimum here is 16. So minimum of 16. Our median, so this is 21 games. So our median is right here in the center. Okay, and then I should have 10 data points on either side of it. So these sets to the left and to the right, they are now even. So my Q3 is going to come from between those two, and my Q1 will come from between the 25 and the 26. And then my maximum is my last point up here at 73. Okay, so I need to check for outliers because I need to know how far my whiskers are going to go. Okay, and then I need to determine if I need to plot any outliers past that. Okay, so as we're checking for outliers, remember it's our 1.5 times the IQR. Our IQR in this case would be 45 minus 25.5 or 19.5. Right, so we have 25.5 minus 19.5, which gives us 3.75. And then we have 45, my Q3, plus 1.5 times my IQR, so 19.5, which is going to give me 74.25. So I don't have any outliers in this particular data set. So no outliers, so I don't need to worry about that. So when I draw the box plot, remember I've got my... All right, so I've got the left side of my box is my Q1 here. The right side is Q3. My median is the line in the middle of the box. And you'll notice these are lined up and these are to scale, right? This line on the left is at 25.5. The line on the right is at 45. My median is at 34. My maximum value for this data set was 73. Okay, so my whisker only goes to 73. It does not go all the way to 74.25. That just indicates that anything above that would be an outlier. Okay, so my whisker stops at 73 because my data set stops at 73. Same with the minimum being down here at 16. Okay, so what you can see if you notice by looking at this particular data set, this data set would be skewed. Okay, if we calculated the mean for this data set, it would be larger than the median because this data set would be, here we go. This data set would be right skewed. And so our mean would be further down the tail. Okay, so it would be a little bit bigger. But this big, huge whisker here, compared to the whisker on the left side, lets us know that this data is going to be skewed. Okay, so box plots are pretty good for comparing data sets. They don't give us super detailed information, but they're good for comparing two data sets to one another. Like if we look at what we have going on here, these are the two travel time sets. Okay, and so you can compare the two to one another. So for instance, if we look at the shape, you can see that both distributions are right skewed. For both states, the distance from the minimum to the median is much smaller than the distance from the median to the maximum. You notice they are comparing the two. They are comparing and contrasting the two. They are not just saying this is what it looked like in New York and this is what it looked like in North Carolina. Okay, our center here, it appears that the travel times to work are generally a bit longer in New York than in North Carolina. Okay, so they compared them a bit longer in New York. The median, both quartiles, and the maximum are all larger. Remember, if you don't use those comparison descriptive words, you will not get credit. You cannot describe them as two completely separate things. Okay, as for spread, travel times are also more variable in New York. So there's our comparative term there. They are more variable. Okay, and then it explains why they are more variable. They're more variable because my length of my boxes are larger, which means my IQR is longer, and my overall range is longer in New York. So I have a wider spread here of my data. Okay, and then we have outliers or unusual features here. The maximum travel time of 85 minutes is an outlier for the New York data. Okay, so that one would be an outlier. And then there were no outliers on the North Carolina sample. Okay, so one last example. I know it's been long, but hang in there. Let's look at this one last example. Again, if you can pause it and do it yourself, that'd be awesome. Okay, so 2011 roster of the Dallas Cowboys included 8 offensive linemen, and here are their weight in pounds. Do the 5-number summary for these data by hand. Show my work. Well, the first thing I need to do is I need to put this data set in order so that I can do that. 307, 307, 310, 324, and then 345. Okay, so there are 8 offensive linemen here. So if I'm doing a 5-number summary, I need my minimum, which is 290. I need Q1. I need my median. I need Q3, and I need my maximum. Okay, where my maximum is 345. This is an 8-number data set here. 1, 2, 3. So here is number 4. 1, 2, 3, 4. There's 4 on the other side there. Okay, so in between 307 and 307 is still 307. Okay, so I have a median of 307. If I come down here to find my Q1, I need my median of this particular data set, which would be 303, right in the middle there. Okay, and then I need the median over here on the right of this particular data set, which is going to fall right here in between 310 and 324, which is going to be 317. So there's my 5-number summary for this particular set. Now I've been asked to calculate the IQR and interpret this value in context. My IQR, remember, it's going to be 317 minus 303. So my IQR is going to be 14 pounds. I'm going to give it unit because I'm giving context. My IQR is 14 pounds, which what that means then, I'm interpreting in context, the range of the middle half of the data, of this particular data, which is the weight of the 8 offensive linemen on the 2011 Dallas Cowboys roster, okay, is 14 pounds. Okay, number 3 asks us to determine whether there are any outliers using the IQR rule. So if I'm looking for outliers here and I'm using my IQR rule, right, I need to do Q1 minus my IQR, which was 14 times 1.5. Q1 was 303. So that gives me that gives me 282. Okay, and then my Q3 plus 14 times 1.5. Q3 was 317. So that gives me 338. So anything below 282, okay, and anything above 338 would be considered an outlier. And in this particular data set, we have this guy that is 345 pounds. So he would be considered an outlier. Okay, and then the last step here is to go ahead and draw our box plot. So when we're drawing our box plot, remember I need to go ahead and I've got a scale here, right? I've got weight and it's in pounds. Okay, and let's see, what's my smallest here? The smallest guy is 301, so let's go 290, 300, 300, 310, 320, 330, 340, 350, and that should be big enough. Okay, and so my first line is at my Q, and so I'm referring back to my 5-number summary, right? The left side of my box is at my Q1, which is at 303, so I don't know about there. Okay, my right side of my box is at my Q3, which is at 317, so let's go with about there. So here's my box. My median is the line in the middle of my box, so 307. So here's my median there at 307. My whiskers go out to my IQR. My edges of my IQR, sorry, they don't go out to the edges of my IQR. They go out to my data points that are equal to that 1.5 times my IQR that follow that IQR rule. They go out to my biggest and smallest data points there. So, for instance, my whisker to the left, my smallest one is 2. I'm sorry, I did have a guy that's 290. So a guy that's 290. So I've got a whisker that goes out there. Okay, because 290 was not that would not qualify as an outlier. Okay, my biggest value that is not an outlier is 324. So I'm only taking this whisker out to 324. Okay, and then I have my outlier out here at 345. So my box plot would look something like that. Okay, so we'll be practicing with all this stuff in class.